All right, so we're going to continue with finishing up the last recorded lecture for DSC40A, and we'll finish it off by going over Naïve Bayes a little bit more using a different example, and we'll review a couple probability problems that will show you how to use things like Bayes' theorem and the law of total probability in some creative ways, and that will kind of show some of what we might be asking on the final exam. Okay, so just to recap from last lecture, the important thing with Bayes' theorem is that we're trying to predict for some sort of class. In the case where we had the example we used in last class was whether there was an avocado that was ripe or not ripe. So those were the classes that we're trying to predict, and the feature space, or our features, were our x's, which were things like the type, the softness, and then color. And we also saw that we really didn't need to calculate the probability of features as denominator because it was the same for all classes. But what we did need to predict, or what we did need to figure out, was the probability of features given the class. And it was nice that we were able to make an assumption here. And the assumption was that this was conditionally independent, which allowed us to kind of expand out that probability calculation and make it a lot easier for us to have that assumption. So ultimately, what we were trying to do was to predict the most likely class based on this right here. And we also saw that we could do this for both a feature or a features. So for example, I believe it was, we had the probability of, we'll just say Haas firm, and then green black, given that the avocado was ripe. And this was in our numerator, so this kind of was that. And we were able to expand this out to consider each of these being conditionally independent. So remember, that would have been the probability of Haas given ripe times probability of firm given ripe times probability of green black given ripe. All right, so that's basically what we focused on in last class. We saw how we could use Bayes' theorem to predict what our class was going to be based on the features that we had, and those features, or that specific combination of features that which map to a class, didn't need to be an actual example in our data set as well. So we also saw how to deal with that with smoothing, because if not, there would have been a multiplication of a zero in the numerator. Okay, so let's talk about today's problem. This is going to be probably one of the more classical approaches to teaching Naïve Bayes. And what I mean by that is that oftentimes in machine learning, you'll have these sort of gold standard training data sets that we use for educational purposes. And you'll see things like the iris data set, which has flowers, or you'll see things like the number classification data set, so the handwritten digits MNIST. And for these kind of Naïve Bayes text-based approaches, you'll see, you'll encounter this most likely in a DSC80 as well, the news group data set, which is just a bunch of news articles that have a class. I believe there's 20 classes in total. So anyways, we're going to be doing text classification, and specifically, we want to take this text data right here, which these are emails. So you can see this is like the subject. This might be a part of the text, or sorry, this is the sender, this could be the subject, that the text might be hidden, and this is the time that it arrived. And so when we're looking at using emails, we're trying to build a spam filter, and this is known as a spam or ham, or the spam ham problem. Spam being the email is spam, ham being that the email is not spam. Why call it ham? I'm not sure actually, but if you know or find out, please let us know, because interested to learn. But we want to try and represent text data now as numerical data somehow, and because obviously a computer can display text and work with text, but it can't process text as numbers, and we're doing probabilities here, so we need numbers. And there's lots of features that we could use. For example, emails have metadata. They have HTTP headers and other features that are part of the email that we could use. A lot of modern day spam filters will try and determine if an email should be spam based on the sender's reputation for how often their mail gets flagged as spam. Obviously, if the user marked an email from a sender as spam before, it's highly likely that that sender will be marked as spam next time. But in today's example in class, we're just going to consider using text. So you could imagine maybe the subject line of the email, or possibly the body, the text body. So we'll talk about how to do that. So this is a method called bag of words, and there's many ways to take textual data or freeform text data and create numerical data out of it. But what it really boils down to is we're trying to create vectors that represent the text in some form. You may be familiar with something called one-hot encoding, and that's something similar to what we're doing here, but one-hot encoding really tries to take categorical data and turn it into numerical data. So for example, you could have, just as an aside, you could have the category for let's say we're doing something with weather maybe, and we could have something like sunny, cloudy, and rain. And what we could have for that is well, this is our data, and this is let's say, and this is an X, and then this is our observations. So we have these three categories, and we could say this as is sunny. Let's write this a little better. Is sunny, is cloudy, and then is rain. And let's just assume that this was our X1, and this is our observation 1, observation 2, and observation 3. One hot encoding would turn this data into essentially is sunny. This observation is sunny, so that I get a 1, 0, 0, cloudy, 0, 1, 0, rain, 0, 0, 1. And if we had any number of data, however long this is, we would keep going. Like if we saw another sunny again, then we would just do a 1, 0, 0. And then we're essentially creating vectors of our data. However, one hot encoding is just a way to take categorical data and then turn it into numerical data, because a computer can't process sunny or cloudy or rain. It needs to have numbers to do that. So this is one way of creating vectors or numbers from categorical data. But what we're doing is called bag of words. So here we're trying to look at the emails that we have, and we're trying to identify emails that have certain keywords. So we create a dictionary of words, and the dictionary that we create is going to have words that we believe could be representative of, let's do this real quick. Could be representative of words that are typically spam. So, for example, we could have a dictionary with the words H and then O, like the number O. Let's just assume case and sensitivity as well. So home, free, and then sale. And I suppose these are strings. So let me put that around it. Okay. So home, free, sale. This is our dictionary because these are words that we believe they have something to do with spam. And let's also just give these an index for quick reference. We'll not use zero-based indexing, it's just one-based indexing. So 1, 2, and 3. And let's say that we have a sentence that we get, or like a subject line of an email. Let's see. I don't know, something like, and this is the email subject, like act fast now, free items, available. So, this is kind of spammy, but in our dictionary we'd say, okay, we identified the word free, and maybe let's add one more actually, just so that we can just say no sale for the hell of it. Okay, so sale. So this is word 2 and this is word 3. So we would say in this case that our x vector is equal to, well, we have 3 numbers we have to put in. So did we have the word home? No, so we get a 0. We had the word free, and free is at index 2, so that gets a 1, and then sale gets a 1. So this x vector here is now a numerical representation of this subject line. Now, is it perfect? Is it exactly represented? If we want to exactly represent this, then we could just use the binary representation of each of these letters or characters. But what this x vector is doing is it's representing some feature of the sentence that we've deemed that we care about. Particularly, does the sentence include at least one of the words in our dictionary? When you get into more complicated or complex modeling with Naïve Bayes or with text classification, you will care more about things, for example, like frequency. This is something called like TF-IDF, term frequency, inverse document frequency, which is a way of looking at the co-occurrence of counts of words in a text. So, for example, like the word "the" occurs in a text quite a bit, so it's not a very important word. And if it's not a very important word, it probably doesn't tell us much about the article. But the word, like let's say, presidential debate, or debate is a word that doesn't occur very often, so it's more of a scarce word, and so it's a very important word probably, and it probably tells us a lot about the potential article that word comes from. Maybe it's like a political article. So frequency becomes very important. But for now, we're just looking at, does the word exist? Does a word in our dictionary exist in this sentence or this email subject? And if it does, count it. And then, of course, these x vectors have a shape of d by 1, because d is essentially however many words we have in our dictionary. And we're going to have many instances of these vectors, basically for however many spam emails we have. We'll have, many more of these. So if the word is present, then put a 1. If it's not, then put a 0. And, like maybe I'll highlight it just to make it really clear. Like x1 index belongs to the word home, and second index belongs to the word free, so on and so forth, so that whenever we're creating our X vectors for a new email subject, we're going to just fill these in with ones or zeros based on, does the corresponding words here occur in our sentence? And that's all. So let's do an example of this. Here we have 5 emails, and we'll just say that these are the subject lines to make it easy. So our dictionary includes prince, money, free, and just. So what does this look like? Well, let's create a chart or a table, and let's have the table be rotated slightly. So we're gonna get these X vectors eventually, but we're gonna store the data as if we're rotating, so that instead of having observations this way, we're gonna have observations this way, and then our columns will be like the x1, x2, xn. So let's go ahead and build that. Okay, let's do, we have 5 sentences. So we have 1, 2, 3, 4, and 5. So we will have 1, 2, 3, 4, 5. And actually, let's save some space at the top. 1, 2, 3, 4, 5. And we're going to take our dictionary now and put the words spanned across the top. So let's put, we'll just start prince, money, free, and the word just. And then of course we also want to know what the class is. So is spam. Okay, so let's fill this out. I am the prince of UCSD and I demand money. There's nothing wrong with that email. I mean, personally, I like that. I like the message. Okay, so does it have the word? So just to be clear, we're sentence 1, so we're filling in this row. So we'll do ones and zeros. I am the prince of UCSD and I demand money. So the word prince occurs. So 1, money, 1, free, 0, just, 0. Well, we have 2 in here, and we know that the label of the email is orange, so it is spam. Okay, Tapioca Express, redeem your free Thai iced tea. I've been to undergrad and a grad student. I teach UCSD. I ain't never gotten a free Thai iced tea from Tap Express. So that's definitely, I don't care what it says, that's spam. But let's do our counts. Prince 0, money 0, free 1, and just 0. But this was classified incorrectly, I think at least, as a ham, so not spam. DSC10, free points if you fill out your sets. Yes, I'm a big fan of free points if a large portion of students fill out sets, because feedback is important for us, and students, like to see feedback. So the word prince, nope. Money, nope. Free, yes. Just, no. And this is marked as not spam. Click here to make a tax-free donation to the IRS. Yeah, sure. That's definitely, that's probably not spam either, to be honest. The IRS probably getting out there and asking for donations. So click here to make a tax-free donation. Free. And 0 for these. And free career night at Prince Street Community Center. And this was classified as ham, so not spam. Let's see, out of these 5, we had 2 spams and 3 hams. So if we're trying to create, let's say, our design matrix, we would need these x's. And so in this case, x of 1 would be something that goes like that and would rotate to something that goes like that now. So this would be, let me just move that over a little bit. 4 numbers, in this case 1100. So 1100. So that's what's happening. Really, this is our x1, x2, x3, and x4. So yeah, I mean, these are our the x's get kind of confusing because it's x's are our observations. We have n number of x's, but then we also have an x for each feature. So these are essentially our features, and then these are our observations. All right, so let's talk about naive Bayes for spam classification now. So to classify an email, we're going to use Bayes' theorem, and we're going to try and calculate the probability of spam given the features and ham given the features. And the one that has larger probability, we'll say that's the correct one. And remember, unless you want to actually know the probabilities out of this and not just know what to predict, we're not going to need to calculate the probability features, though you can if you're able to, and you can get out the actual probabilities from it. But what we're really trying to do is figure out what that is. So that's what we're going to aim to do. And remember, we have this thing here, which is proportional to. And that's just, each one of these corresponds to this. Because what we really care about predicting are these things. So we just need to deal with the numerator, which will require us to calculate each of these separately, which each of these is essentially this, and then the numerator that's higher is the one that we will predict for this class. All right, so let's take a minute or so and think about this. We have the probability of features given spam, the probability of features given ham, and then we have the probability of spam and the probability of ham. Which of these probabilities should add to 1? So 1 and 2, features given spam and features given ham. So this is equivalent to saying the probability of we'll just call it arbitrary word given spam plus the probability of arbitrary word given ham, equals 1. And remember that this and this, same word. Okay, so this can't be true because this thing can equal more than 1. And if we think about using a very common word like the word the, so example, the word the is highly likely to occur in both spam and non-spam emails, right? So by that very case, those two probabilities, like let's say there's a 95% chance that the word the is in a spam and a 95% chance it is in the word that is in a non-spam email, that means that the probability would be greater than 1. So that means that this is out, and that also means that this is out. So it's either got to be B or D. So let's look at 3 and 4 together. And let's write this out. So this is essentially saying the probability of ham equals the complement of spam. And this winds up being true because in this sort of world case, we really care about an email is either spam or it's not spam. It's ham or it's not ham. You can't have a world in which the email is neither spam nor ham. It needs to be one of the, it's not a Schrodinger's cat type of situation. It must be one or the other. Therefore, both these probabilities must add up to 1, or should be 1. So that's gonna this is our answer. And another way to think about it it would be the probability of this arbitrary word given spam plus probability of and this or a C is both complement. Is here written as both ways. The word, not the, but this arbitrary words complement given spam. That could have equaled 1 as well, but this is not the same thing as this. So that's just something to keep in mind. The reason why being that the classes are different. This is an occurrence of a single feature in one class. That feature is either in the class or not. Therefore, it equals 1. Okay, so in order to estimate the probability of ham or spam, we're going to need to compute something, and that's going to be the number of spam or ham emails in our training data set. By training data set, that just means our x's. The matrix of, you say xi's and x. Well, I suppose x represents the entire training set, and the number of emails that have either been categorized or classified as ham or spam is a subset. So spam class emails and ham class emails, both of those are subsets of X. And we also want to think about the probability of the features given spam or ham, and that's where that conditional independence is going to come into play. So let's take a look at how that works too. So in this case, remember we have the assumption, the naive assumption in naive Bayes is the conditional independence, and that means that there's the chance that given a class, spam or not spam, there's the eventuality that a feature will not occur in that space. And since we have conditional independence, we're taking the product of these probabilities and multiplying them. We're going to have a 0 at some point. So we will need to deal with that, because in this case, our x1, which is essentially our training data, and that was something like the word home or the word free or the word sale, because those correspond to our x1, x2, and x3, x3. There's an eventuality where one of these or many won't be in one of our observations, and that observation matches up to one class in our training, because it's supervised learning, so we know the answers. So that's why it's important that we know how to deal with that, which we've talked about that before. And just to make it clear where this maps, you have that and this, and that maps to these things right here. And this is really being driven by the features. So in this example, training example is labeled as spam. It's the given class has word 2, right? 2, but not word 1. All right, so let's go back to our example. So this is the training data set that we had, and it's a training data set because we know the answers. We'll say, so spam 0, 0, 1, 1, 1. So you could imagine this as our y's. In this case, the y vector would equal 0, 1, 1, 0, 1. All right. And let's also go ahead and copy this. I don't want to draw it again. You don't want to see me draw it again. Let me delete these things. This will only confuse us. Unfortunately, I'm going to have to delete those all the way through. Anyways, okay, so we have this new example here. We have a new email to classify, and we have a subject header, download a free copy of The Prince of Persia. Okay, so how are we going to classify this email given what we already know? And let's remind ourselves again that we have our dictionary of prince, money, free, and just. This is our dictionary. I won't write like code, more confusing. Okay, so let's look at this email. The word prince occurs once, money, nope. Free, yep, and just, nope. So this is a 1010. Okay, so the first thing we need to do is to think about what is it that we're actually trying to predict, and want to think back to, where is it? This slide right here. Particularly these guys. Okay, so this is going to be the probability of spam given features. And we're going to say the probability of spam times the probability of features given spam. And then we're going to be able to expand this out. And so we're going to have, I guess we can do it down below. This will be the probability of spam, because this just comes down, and that's going to be the whatever part. The part that's interesting though is the probability of features given spam. So by the rule of conditional independence, we can pull this apart and turn them into the products of each of the individual features given or given spam, because we wanted to classify this. So again, we're looking at spam first. Okay, so this is going to be the word we're going to do this for each of our features. So prince being true given, because that's the important part. And the reason why the prince equals 1 is because when we're looking into our training data, we want to think about the probability that we have a spam email where the word prince is true. So in this case, we have 2 spam emails, and prince was true only once. So that's not a really good weight to kind of convince us either way that the word prince being in like an email is evidence of it being spam. However, that's from the spam's point of view. From the ham's point of view, the word prince never occurs at all. So, yeah, it does. So if it didn't, though, then that would provide rich information to when we're looking at this from the not spam point of view, which we'll calculate that next. But so 1 there. So, all right. I'm going to use shorthand for the rest of this. So the probability of the word money equals 1 given spam times the probability of free equals 1 given spam times the probability of just equals 1 given spam. Okay, so let's just, we're looking at spam, so it's always nice to highlight these things. It can help. So we care about these and these right now. So this is just going to be probability of spam is 2/5 times prince. Well, we already saw it was 1. That was the hello. That was the half right here. And now let's kind of go through the rest of these. Times 1/2 times, this is also 1/2, and we're just, I wrote that wrong actually. This should be equal to 0. And money is equal to 0 as well. I wrote that wrong as well. Got ahead of myself. The reason why money and maybe I'll just highlight this to make it easier. The reason why money is 0 and this is 0 is because this is 0 and just is 0. I kind of did a little backwards because there's nothing to highlight here, but that comes from, I was highlighting the entire sentence from this. And since I already highlighted or underlined that as being black, Prince and free, and then Prince and free. So hopefully you can see that this, or sorry, this and this and this and this and this and that. Free, free, free. Okay. Where was I? All right, so this is going to be, we're just equal to 0 for span, both 0. So 2 over 2, effectively 1. So 2/5 times 1/2 times 1/2 times 1/2 times 2 over 2. Let's see. 1 over 20. All right, now let's go ahead and do this from the point of view of ham. So just like before, we will highlight all the occurrences of ham. So that's this one, and that's this one, and that's this one. And I can probably just quickly take this. All right, this we have it. So I'm going to use shorthand again, because why not? So this is the probability, same thing of, this is bothering me, so let's take care of these guys real quick. Okay. This will just be the probability of ham now instead of spam, and that was what, 2/5, so this is going to be 3/5 times the probability of Prince occurring given ham times the probability of money equals 0 given ham times the probability of free equals 1 given ham times the probability of just equals 0 given ham. So again, the 0s and 1s just come from over here. All right, so this is 1/3. This one is 3/3, and is it technically divided? Free equals 1. Well, we have the word free in all of them, so this is 3 over 3 again, and then just equals 0. Just 0, 0, 0. 3 over 3 again. So we got a lot of 1s. So we'll say that this is equal to 1 over 5, I believe. And that's 1 over 5, and this is 1 over 20. So we'll say 1 over 20 for spam, and 1 over 5 for ham. So looks like we are getting a free copy of Prince of Persia because we're voting for ham. It is not spam. So, very good. All right, let's flip the script a little bit. Actually, before we do that, let me. Let's rewrite it. Okay. Now the sentence, or the email, sorry, is just what's your price, Prince? So we're going to have an occurrence of Prince, no money, free, and just. So R1001. All right, let's, hopefully you can see where this is going. If you paid particular attention in last lecture, but this is spam given features, and that's going to be the probability of spam times, and then probability of Prince equals 1, looking at our chart over here, given spam times the probability of, we already did Prince, so this will be now money. And that's going to be a 0 because you didn't have any occurrences of it, given spam times the probability of free equals 0, given spam times the probability of just equals 1, given spam. And these numbers doesn't really matter because this guy over here equals 0. This is our fly in the ointment, as they say. So we get the because of this guy right here. Okay, and what did we learn in last class to deal with this? Smoothing. Smoothing is something that there's different approaches to it, and it's sort of like no reason not to do smoothing, even if you kind of believe there's no reason that you might need it. It's just good practice. Remember from smoothing lecture that this component right here is our total number of spam emails, and we're always adding +1 to the numerator, but we add a, let me just use red, use yellow. So this is a +2, and that's for each feature. Okay, and we're adding that so that we remove the possibility of multiplying by a 0 in the product of the conditional independent probabilities in the numerator. All right, so let's go ahead and try this again. Oops. So now let's add smoothing, and this is going to be well, let me highlight these to make it easy. So this is doing it for spam. So okay. 2/5. Remember, we don't add smoothing to this probability of the class. It's only to the conditionally independent probabilities. So this will be 1/2 + 1 plus, remember, 2. We have 2 classes, times 1 + 1 over 2 + 2, 1 + 1 over 2 + 2. This will be 0 + 1 over 2 + 2. And this is going to simplify to 2/5 times 1/2 times 1/2 times 1/2 times 1/4. 2's are gone. It's going to give us 4 times 4, 16 times 16. Yeah, 5 times 2, 10 times 2 times 4, so 180. All right. Now let's try the same thing, but for the other class. And I'm going to use a lot of shorthand on here. Please bear with me. I actually do purple this time. So this will be the probability of ham given our features is going to be the probability of ham times the probability of prince equals 1 given, remember we're doing ham now, times the probability of money equals 0 given ham times the probability of free equals 0 given ham times the probability of just equals 1 given ham. And the calculations for this are very straightforward. So that's going to be 3/5, I believe. Let me just do this for ham, that guy, this one, and that one. Times 1/3 plus our smoothing factor times 1 plus our smoothing factor, 2 over 3 of them, plus 0 over 3 plus 1 plus 2, 0 plus 1 over 3 plus 2. It's going to equal 3/5 times 2/5 times 4, 4/5 times 1/5 times 1/5, which is going to equal 24 over 5 to the 5th, which is a large number, something 3,000 and something. Let's do it real quick. Okay, 3,125. So then that would just go down to being 1 over 80. Okay, so we have 1 over 80, and we're comparing that to, oops. We're comparing the, I'll just write it down. It'll be easier. I'll do it in, how to do that one in red, okay. So again, that was 24 over 3,125, and that is going to be compared to our 1 over 80, which was spam, and what we have here is ham. So in this case, 1 over 80 is larger, so we will predict spam. Okay, so hopefully that shows you another example of a naive-based problem using data that's slightly different than what we've used before. We had to kind of wrangle it and deal with it, and the big departure here was that we wind up counting these for individual thing that we're trying to classify. And then we have this equal sign here in the independent conditional probabilities for the occurrence of the feature given that class. So the occurrence of the word free, that feature given we're in the ham class. Okay, now going forward in other classes, this will begin to get very complicated very fast, as we're not going to be using bag of words, but we'll be using things like sequences of words. These are known as like bigrams, or n-grams is a more general description. So you have a word, plus a word, so this is a bigram, because this is a 1 and a 2. And then you also have a word plus and 1, and this is an n-gram. And n-grams and bigrams are just words that go together, like, for example, dependencies between. This is a token, would be a bigram, and then this would fall into the category of like an n-gram. Because if we know, I believe it was Adam Firth or somebody's named Firth who said that, how did the quote go? It was, you shall know a word's, maybe it was meaning or definition, or I think it's just that you shall know a word by the company it keeps. I think that's it. Let's go. Earth, you shall know. You shall know a word. You shall know a word by the company it keeps. Yeah, John Firth. There you go. So what that means is that how you really wind up, let's say, predicting the category of an article is not so much by the occurrence of arbitrary words, but oftentimes better things to do are to look at the co-occurrence of words and words that are together. Because when you have words that are together, you have the ability to build context. And words take on many different meanings. Like you could have, you might say like an occurrence of the word family is generally, maybe not for some people, certainly have my issues, but you might say that the word family is positive without context. But what if that same word actually occurred in the sentence like, I hate my family or something like that, right? So in this case, this trigram, this would be is actually very negative. So context is very important, extremely important. And that requires, it's not so much that the modeling in the machine learning algorithm, especially for something like Naïve Bayes or these kind of algorithms, is that much more difficult. Of course, if you're dealing with like deep neural networks, LSTMs, long short-term memory models that are deep neural networks, or recurrent neural networks, RNNs, or even ChatGPT. It's those models are more complicated, but it's really the word processing that becomes a big task, and finding really good vectors. Remember, the vectors that we created were just simple occurrences of a word, zeros and ones, but embedded word vectors where you have very large vectors that represent a word based on perhaps co-occurrence counts or something like that, are much more richer vectors for words, or much richer representations numerically of words in m-dimensional space. And that is a big step towards providing you a better method for dealing with text classification, but beyond the scope of this class. Okay, so depending when you watch this, we might have already done the Naïve Bayes classifier in class, and if so, hopefully that was helpful. If not, you can review the demo code on the website, but basically we just coded up Naïve Bayes and took a look at it, and then talked a little bit about modeling in general and the output of a model and how you evaluate it, things like confusion matrices, accuracy, stuff like that. Okay, so to round this off, just do a couple quick problems. So things are interesting. Suppose you're given the following probabilities. Probability of A given B is 2/5, B given A 1/4, and A given C is 2/3. So A and C are independent. What is the probability of B? So the approach to this problem is can be tricky, but you always have to look at what you're given, and that's that A and C are independent. So we know that we want to use Bayes' theorem for this, and the reason why we want to use Bayes' theorem, well, let's just write it down. A times the probability of B given A over the probability of B. So why this is important? Well, quite frankly, because I already have most of these things right here, right? Like we're given the probability of A given B, given the probability of B given A. All we're looking for is the probability of B, and we can calculate the probability of A actually, especially if we can rearrange Bayes' theorem a little bit. For example, we can rearrange Bayes' theorem to be the probability of B equals the probability of A times the probability of B given A over the probability of A given B. And we also know that since A and C are independent, what else can we do? Let's see. A and C are independent. So we know we're trying to fill in this stuff, and particularly we're trying to fill in. We turned it into this form because what's the probability of B? This is what we're trying to solve. But if A and C are independent, what does that mean that we can do? It means that in our case, the probability of A given C is equal to the probability of A. And those are from the last couple lectures. You saw how that works. And that equals 2/3. So currently, we have the probability of A. We have the probability of, that's the probability of A right here. We have the probability of B given A. And we have the probability of A given B. So we can now just plug these probabilities in, and we'll see what we get. So the probability of A is 2/3 times B given A is 1/4 over 2/5. 2/5 there. Turn that into a 2, that becomes a 1. This becomes 1/6 over 2/5, and this is going to be something like, yeah, we can take this down with the reciprocal. So 1/6 times 5 over 2, which equals 5/12. Good enough. Okay. And the next part of the problem, this will be the last one that we'll do because it's going to go long. I think this is the last one, right? Yeah. Okay, so now suppose A and C are not independent, and the probability of A given the complement of C equals 1/5. Given that A and B are independent, what is the probability of C? So, well, since these are, since A and C are not independent, it's 1/5 and 2/3. Okay, so here's the first thing that we can do real quick. Just from reading this, given that A and B are independent, so that means that we can do, we can work on these two. So this would be equivalent to now the probability of A is equal to 2/5, and here the probability of B is equal to 1/4. All right. So what is the probability of C? Well, let's start by using the law of total probability and say the probability of C is equal to the probability of C's intersection with A. So that'd be plus the probability of C's intersection with A complement, and that would be equal to, so this expands out with the law of total probability. Probability of C given A times the probability of the complement of A times the probability of C given the complement of A. And I really can't go further there. What we do know is the probability of A, so we can extract that out and rearrange this a little bit so that it's now the probability of A. So I mean, what we're trying to do is we have unknowns that we're trying to track down and seeing how we can rearrange stuff. is, again, now would be A of C plus the probability of complement of A. No, in this case, this would be actually the complement of C. So BA of C, and this is now the probability of C times the probability of A given C plus probability of the complement of C, because yeah, that's reversed now, times the probability of A given the complement of C. Okay. We know A is 2/5, so we can put that in. A 2/5 equals, since those are independent, that would be 2/3. So the probability of A given C would be now probability times 2/3 plus, this is going to be 1 minus P, I believe, because the total probability, and that would be multiplied. We already have the 1/5 because we know that from the given, which is right here. So we can shove that in there, and we're going to have to also state that we're letting P equal the probability of C. Okay, so we really can't go any further with this, actually, I think. We just need to solve for P. But sometimes knowing that you can't go for any further is also important or good, and I believe in this problem this is as far as we can go with the givens that we have. All right, so that's all the new material for 40A, so congratulations. I'll go over some new stuff in the demo if you haven't seen the demo yet, but you won't be tested on the things like confusion matrices and stuff like that. If there's something that you're not going to be tested on, I'll let you know in the class demo, or if you haven't seen it, I don't know what to tell you. I guess you won't know anyways, but yeah, we'll try and, I will get a Zoom going for that demo. So we'll try. Okay, this has gone on long enough, so thanks for watching the last recording of DSC40A, and then we'll see you for the final lecture live when we also do our mock final exam on the last day of class before the final exam.